Dear students, welcome you all for another video session on the topic race-free state assignments. Students, we already spoke about what is race. We already discussed on critical and non-critical races. So let us see how to overcome the race, and let's see about the race-free state assignments. Okay. So what is this? So let me write that for you all. When two or more binary state variables, change in response to a change in input variables is what is called as race, right? We already discussed this in the previous topic, right? When two or more binary state variables change in response to the change in input variables is called as race. Okay, so we should avoid this race, otherwise it will end up in the wrong state, right? So this is very important. So to overcome this, we have to find out how exactly the race is causing the wrong state and how do we make a circuit race free. Okay, so there are two methods or two types of eliminating the race. The first method is called as shared row method. This is the first method, which is called as the shared row method, and the second method is called as multiple row method. So these are the two methods that we will see today to overcome the race. Okay, how to eliminate the race. So let us first discuss on the shared row method. So I'll give you an example so that you'll understand it better. So coming to the first type of shared row assignment or shared row method. So in this, consider four states. Okay, so my four states I'm considering as A, B, C and D. So let my inputs be 0, 0, 0, 1, 1, 1 and 1, 0. So these are my inputs. So I am considering like my input A, when that is my state A, when the input is 0, 0, it is going to the state B. I'm just considering an example. Okay, so all this we have already discussed in the sequential circuits, right? So A, when the input is the state A, when the input is 0, 1, it is going to the same state. So I'll say this is a stable state and then encircle it. And A, when it is 1, 1, say it is going to the state D. A, when it is 1, 0, it is going to the same state, so I'll circle it. So B, when it is 0, 0, it is going to the same state B. B, when it is 0, 1, it is going to D. And B, when it is B state, when the input is 1, 1, it is going to the same state B. And here it is A. Similarly for C, when the input is 0, 0, it's going to the same state. And here let me say as when it is 0, 1, it is going to A. 1, 1, it is going to B, and 1, 0, it is going to the same state. D state, when the input is 0, 0, it is going to C. Here it is going to the same state. Here again it's going to the same state, and let me write it as C when the input is 1, 0. Okay, so these are our four states, right? These are our four states. So let us solve the shared row method. Okay, so from this, let me draw the transition table. Let me draw this transition diagram. So dear students, concentrate here. So let me consider A over here, B over here, C over here and D over here. So let me write these inputs as 0, 0, 0, 1, 1, 1 and 1, 0. Okay, I'm just assigning the values here. So when there is a transition, right, from A to B, there is a transition here. So when I'm saying A to B, there is a transition. So the input of A is 0, 0 and the input of B is 0, 1, right? So here there is one position change, right? Say there is no problem. So I'll just move a transition from there, okay? And I say that from A to C there is a transition, okay? From A to C there is a transition, okay? I'm just writing A to C there is a transition, and say from C to B there is a transition, okay? And I'll just write this and I'll explain to you all. From D to C there is a transition, and again from A to D there is a transition, okay? You can see here A to B there is a transition. I'm moving from A to B, I'm moving from A to D, I'm going from A to D, I'm going from B to A. So from B to A again there is a transition. You can see this diagram and you can correlate with this transition diagram. So A is moving to B, so I've written A is moving to B, okay? A is moving to D, so A is moving to D, so the arrow is pointing over here. So B is moving to D, so B is moving to D here. So B should be moving to D here, okay? So B is moving to D here and B is moving to A here, okay? So B is moving to A here. So I pointed out my arrow like this, right? C is moving to A, so C is moving to A, okay? And C is moving to B, C is moving to B. So here C is moving to B, and D is moving to C, D is moving to C, and yes, and B is moving to D. So you may not represent the same state, okay? So this is what is the transition table. So seeing our, the state table which I have represented here, I have just reproduced the same using the transition table, okay? Now what you can do is to avoid the race condition, okay? So when exactly the race condition occurs is, so if you're considering the input A and B, if there is one bit change in the position, say here it is 0, 0 and 0, 1, if there is change in one bit, then it has no issues. But whereas if there is change in 2 bits, then a race condition exists. For example, if you take 0, 0, A, if you consider A 0, 0, and if you consider here C 1, 1, you can see there is change in 2 positions, right? 2 bits actually, right? So if there is change in 2 bits, then there is a race condition, and that race condition has to be avoided, okay? So to avoid this race condition, let us go for the shared row method, okay? So when I'm solving the shared row method, let me consider a 3-variable K-map, okay? Let me consider a 3-variable K-map, okay? So here, let me write this for you all. So when I consider the 3-variable K-map, something like this. So here, let me consider the inputs as 0 and 1, okay? And here, let me consider this as A. So we have 4 states, so I'll represent this as A, this as B, this as C, and this as D. Dear students, you can represent the states as you wish, but see to that you represent it in the way as T or inverted T, okay? So I've represented as T over here, A, B, C, and D, and since it's a 3-variable K-map, I've taken the inputs as 0 and 1, okay? So here, I'll name the inputs. We very well know it is 0, 0, 0, 1, 1, 1, and 1, 0, okay? And if I have to assign the value of the cell, then it is here 0, 0, 0, here it is 0, 0, 1, here it is 0, 1, 1, here it is 0, 1, 0, correct? And if it is here, and if it is in the D, then it is 1, 0, 1, correct? So this is how is our inputs named, okay? So let us consider, okay, let us go to this diagram. So let us consider this, okay? So when you consider this, you can see that A is moving to B, right? Here A, that is A to B. So if you are considering A to B, A is what? 0, 0, 0, and what is B? 0, 0, 1. So here there is only one position difference, right? So as I told you, if there is only one position difference, then there is no problem and there is no condition of race existing, correct? So you can just ignore that. Now consider A to D. Okay, if you're considering A to D, now consider A to D here. What is A? 0, 0, 0, and what is D? 1, 0, 1. You can see that A and D is differing in 2 bits, right? 2 bits. So what happens here? We can solve this problem, or we can solve this race condition. Here there is race existing because there is difference in 2 position, right? This race can be eliminated by a method called as intermediate. It is called as intermediate unstable state, or assigning of intermediate unstable state. Okay, so this is the method to be followed. Now A is 0, 0, 0 and D is 1, 0, 1. So here what I have to do is, so I will intermediate, or I will assign an intermediate state to get to D. So from A to D, I'm covering this particular position. Okay, so if I have to take the value of this, what will be my value of this state? So 1, here it is 1, and here it is 0, 0. So here it is 0, 0, right? So you can see that from A to D, I am coming via an intermediate state, that is 1, 0, 0, right? Now if you take this 1, 0, 0 and 0, 0, 0 differs by only one position, correct? So this is called as intermediate unstable state. Okay, here if you take these two, 1, 0, 0 and 1, 0, 1, it differs by one position. So our race problem, or the condition of race, is being solved by addition of this intermediate state, and this intermediate state I shall name it as E. Clear? So this intermediate state I am naming it as E. Now, okay, so this solves the problem of my race condition. Next, now we went from A to D. Next is A to A. So that's not a problem, going to the same state. Now come to the second input, second state B. So B is going to B, so there is no problem. B to D. Let us come to B to D. Now see over here. So it differs by only one position, right? Here it's 0, 0, 1. Here it is 1, not 1. So there is no race condition. So we can skip that. Go to B to B. There is no problem. B to A again. B to A again. There is no problem because it's only one position that is differing. Now come to C to C. No problem. C to A. Now C to A. So A is 0, 0, 0 and C is 0, 1, 1. You can see here there is difference in 2 positions, right? So there is a race condition that is prevailing. So to avoid this rate condition, I'll have to add an intermediate unstable state to eliminate this race, right? So what I'll do is, so I'll consider the intermediate state from here. So let me take an intermediate state from C and let me go to A. Okay, so A to C, right? So this intermediate state comes from C and it goes to A. So this state has a value of 0, 1, 0, 0, 1, 0. Okay, now C to A. So let me name this as F for y'all. Okay, A, B, C, D, E. Now let me take this state as F. Okay, so from C to A, since there is a risk condition availing, so this risk can be removed by addition of intermediate unstable state, which is called as F. Okay, now you can compare this and this. You can see there is only difference in one position now, right? Yes or no? So here, so this eliminates the risk. Now come back to here. So C to A is over, C to B. Now C to B, so C to B, you can see here it is 0, 0, 1, here it is 0, 1, 1. So it is difference in only one position, right? So you can skip that. Now coming back to the last state, D, D to C. If you're taking D to C, what is D? So D is 1, 0, 1, C is 0, 1, 1. So you can see that it is differing in 2 positions, right? Yes. So here the race condition prevails. So to eliminate the race condition, what shall I do? I should include an intermediate state. So I shall include this state over here. Okay, I can include this state over here. So from D to C, it is coming through this intermediate state, which has the value as 1, 1, 1. It has the value of 1, 1, 1. Okay. So the value of this is 1, 1, 1. So let me assign this intermediate unstable state as, say it as G. Status G. Okay. So dear students, I guess hopefully you would have understood how the intermediate unstable state eliminates the race due to differing of two positions, right? So this is what is called as the shared row method. Okay, so here in the shared row method, okay, what I have to do is, after the finding of intermediate states, like I will have to draw something called as the transition diagram. Okay, so from this, let me draw the transition diagram. So I'll rub this for you all. Okay, so the transition diagram now becomes, see, this was before the addition of the intermediate state. Now, after we finding out the intermediate state, my transition diagram will be like A, B, okay, so A to B, okay, A to B I'm taking. So from B to C, okay, from B to C. So from B to C, I'll tell you, let me draw this. Okay, from A to B I'm going, from B to C. Okay, from C to A if I have to go, from C to A if I have to go, there is an intermediate state F, right? So from C to A, I'll have an intermediate state F, and then it goes to A, correct? Then if I have to come to A to D, if I have to come to A to D, there is an intermediate state called E. From there, I'm coming to state D. You can see here, A to D, I have an intermediate state E, so that I'm representing over here. Then similarly, from D to C, see here, D to C. So D to C, if I have to go, there is an intermediate state G, right? So if I have to go to D to C, I have an intermediate state G over here. Then I have to go here, correct? So this is what is my, transition diagram. So I can name here as 0, 0, 0. So 0, 0, 1. So 0, 1, 1. Okay, the values whatever we have assigned. D is 1, not 1. So what is my E? E is 1, 0, 0. So what is F? F is 1, 0, 1. Okay, so this is my transition diagram. So after we eliminating the race, we will reproduce the transition diagram using the intermediate unstable state. So what were all the intermediate unstable state for us? F, G and E. So we have included that. In between A to D, here it is E, right? So E, F and G are three unstable states used to reduce the or to overcome the race condition, right? So after this transition diagram, we have something called as the flow diagram. Okay, it's called as the transition or modified flow diagram. So I'll draw the modified flow diagram for you all. So I shall draw it here. So after the transition diagram, we have to draw the modified flow diagram. So this is your modified flow diagram. So here it is. You have to mention all the states A, B, C, D, E, F, G. Okay. So let me write this states for you all. So how many of our states we have got, inclusive of the intermediate state, we'll have to mention that, and our inputs. So our inputs is 0, 0, 0, 1. The next input is 1, 1, and the last input is 1, 0. Okay. So here, so when our input is, so we know what was A 0, 0, 0. What was B? B 0, 0, 1. Okay. So here it is A, B, C, D. You know what is the value. Okay. So when A is 0, 0, okay, it is going, using our first state table, when A is 0, 0, it is going to be, and A is, it is going to A itself. Okay. So in the next condition, it is going to D. See, when A is going to D, we very well know when A is going to D, it's directly not going, right? It is going through the intermediate state E. So when A is going to D, see here, when A is going to D here, it is going via the intermediate state E. So what I'm supposed to do is, so here A is going to D, I'm supposed to write here as E, because via E it is going here. Then, so come back to E over here. Come back to E over here. Then you have to write here D, because, dear students, concentrate well here. See here, A is going to B. I have written the next state because there is no change in the position of bits. So directly I have written the same. Here the same state A. But when A is going to D, we saw that when A is going to D, there was an intermediate state E. So what I'm supposed to do is, A is going to D via E. So A is going to D through E. Then come back to my state E, and here it's going, or it is ending up in D. Is this clear? So this is how I have to represent my, modified flow diagram. Next, in case A is going to A, so let me write the same. So A is going to A, so this is same for me. Now come to B. So B is going to B. So there's no issues. B is going to B. So B is going to D. Now see here, B is going to D. So B is going to D. So B is going to D. There is no change in position. So B is going to D. So it will be same. Here it is B, same again. So B going to A. There is no problem because only one position. So A. Next, C is going to C. So no problem. Same. C to A. Now consider C to A. When it is going from C to A, you can see that intermediate state F is there, right? So C to A, there is intermediate state F. I'm supposed to write here F. Then come back to F, and you're supposed to write A over here because it is reaching A only after coming through the intermediate state F. Clear? Then C to B. C to B. Where is C to B? There is no change. There's only one position. So you can write B over here. Then C to C. Okay. Then coming back D to C. So D to C. You can see where is D? D to C. It is going from the intermediate state. Dear students, here I have just made a mistake because A, B, C. After C, you have to write here as F. So A, B, C. So here I'll write it as F. Okay. After F, A, B, C, F, E. Here it is G, E, D, G. Okay. So write it in the same order. A, B, C, F, E, D, G. So A, B, C, F, E, D, G. Okay. So for F here, I'm sorry, for the changes which we made for E, here it has to be D. Okay, no problem. For the next, for C is A. For C to A, you can see from C to A, it is going to C to A. 1 minute. So where is C? C is here. It is going to A. So C to A, it has to be F here. We have written it correctly. For F, it has to come to C to A. 1 minute. C to A, it has to go to F. From F, it has to come to A. Yes, it's correct. Okay. Here it has to be A. So now come to the next position, C to B. There is no issues. Okay, we are finished with this. Now come to D. D to C. Now if you are coming to D to C, you can see the intermediate state G over here. So D to C. So intermediate state G I should come. Then go back to G. After going back to G, you will have to write it as C over here. Right? So then come to D. The next position is D. So no problem. So D. So the next position is D. No problem. The next position is C. For C again, D is going through C via G. So you have to add G over here. Okay. And come back to G and write a C over here. Okay, dear students. I guess this is clear for you all. And the remaining position, you can just mark as, a dash. Okay. So this is the shared row method. So you have to just analyze this via the intermediate state. Okay. So this shared row method is very efficient method, and the number of row is also reduced. Okay, the number of states is reduced actually. It's reduced. Here you can get 7 number of states, and this is considered to be the most efficient method to reduce the race. Okay. So let's go to another method which I spoke, which is the multiple row method. Okay. So the multiple row method, I'll explain with the same, example, and we will see what is the difference between the two. Okay, coming to the multiple row method, here again we are considering the 3 variable K map. Okay, so in the multiple row method 3 variable K map, you can see that, okay, here the number of states will be doubled. Unlike the previous method, here the number of states is doubled. So let me consider the 3 variable K map for you all. Okay, so 0, 1, and here it is 0, 0, my inputs 0, 1, and here it is 1, 1, and 1, 0. So 0, 0, 0. So 0, 0, 0. Now let me write it as 0, 0, 0, 0, 0, 1, 0, 1, 1, and 0, 1, 0. Okay. So here A1 is, okay, if I'm considering 0, 0, 0 as A1, okay, and 0, 0, 1 as B1, 0, 0, C1, and this one as D1. Here A1 is 0, 0, 0. When you take the complement of A1, it is 1, 1, 1. So this 1, 1, 1, you can see here, the 1, 1 is this position. So this I'll name this to be as A2. Okay. Now consider the complement of B1, 1, 1, 0. So 1, 1, 0 is here. One start. So if I'm taking A1 as 0, 0, 0, the complement of A1 is 1, 1, 1. So I can assign it over here. Then if I'm taking B1, the complement of it is 1, 1, 0. So I can assign B2 as here. Okay. If I'm taking C1 as 0, 1, 1, the complement of it is 1, 0, 0, which I can assign it over here. And D2's complement is 1, 0, 1, which I can assign it over here. Okay. Now, how will I draw the flow table? This is the only difference between the two methods. The flow table is same like, just write all the states A1, A2, B1, B2, C1, C2, and D1, D2. Okay. And you can write all the inputs. So we are considering the same state table. So here taking out all the inputs, here you have 0, 0, 0, 1, 1, 1, and 1, 0. Okay. So considering this, so for 0, 0, let me consider 0. A1 is 0, 0, 0. A2 is what? A2 is 1, 1, 1, right? So A2 is 1, 1, 1. B1 is 0, 0, 1. B2 is 1, 1, 0. C1 is 0, 1, 1. C2 is 1, 0, 0. D1 is 0, 1, 0. And D2 is 1, 0, 1. Okay. So here, so come back to the state diagram. So A1 is going to B1. There is no issues. So I'll write it as B1 itself. For A1 going to same position, I'll write it as A1. So A to D. Okay. So A to D also has no problem. So I'll write it as D1, and A to A has no problem, so I'll write it as A1. Okay. So B to B, again the same thing is repeated over here because we're taking the complement. So you can write this as B2. So this becomes A2 for the same position, and here it becomes D2, and here it becomes A2. Okay. So coming back to B1, so for B1 it is same state B1 itself. So for B to D, we saw that there was a transition, right? So from B to D, there was transition as what? So for B to D, there was a transition from B to D, there was no transition. So I'll write this as D1 itself. So for B to B, it's B1, and for B to A, it is A1 itself. Okay. So similarly, repeat the same. For B2, it is B2. For D2, it is D2. For B2, it is B2. And for A1, it is A1 because there was no position difference, right? Coming to C1. So for C1, it is C1 itself. For C1 to A, okay? So for C to A, we saw that there was a transition, right? So C to A, there was a transition through the state F, right? So C1 C1. So C1 to, there was a transition. So from C1 to A1, there was a transition. So when there is a transition from C1 to A1, you're supposed to consider the complement of A1. So what is the complement of A1? It is 1, 1, 1. Now if you take the complement of A1 over here, dear students, note that there is difference here between only one position. Understood? So see here. So C1, now here C to A transition, C to A transition, that means C1 to A1. When you're considering C1 to A1, so 0, 1, 1, so here it is 0, 0, 0. So I have to take the complement of A1. The complement of A1 is A2 here, which is 1, 1, 1. So when I consider this, the race condition which is prevailing here is avoided, because when you compare C1 and A2, you can see there is only difference in one position. So here I am supposed to write this as A2. Clear? So this avoids my race condition. And the next is C1 to B1. There is only one position difference, so I can directly write it as B1. Okay? And the next is C1 to C1. Similarly for C2, C2 to C2, I'll write C2 to C2. C2 to A2, you can blindly write as A1, because you can see here C2 to A2. Okay, the complement of A2 is what? Is A1, and 0, 0, 0 and 1, 1, 1, right? So here it is A1. Okay, I can write it as A1, and here it becomes B2, and here it becomes C2. And coming to, okay, so here you can see that this is C2 is stable condition. Okay, here B is the stable condition over here, right? Here again C is the stable condition, correct? Here B2 is the stable condition. Now coming to D1, D1 to C. So here it is no issues because only one position. Here again no issues because the stable state. Here again no issues, stable state. Here again no issues, stable state. Okay. Similarly here C2, here D2, here D2, and here C2, right? So wherever the intermediate state comes, you have to consider the complement of that particular state, and that you have to write here. Okay. So this is what is your method called as multiple row method. Okay. So multiple row method is easy when compared to the shared row method, but the only drawback is here you have 8 states when compared to the previous shared row method. Okay, that's the only difference, and here you have more number of states when compared to that previous shared row method. Dear students, hope you have understood how to eliminate the race by using the shared row method and the multiple row method. Thank you, dear students.